The morning of January 7th, 1945. Somewhere in the frost-hardened forests east of Bastogne, Belgium, Staff Sergeant Michael Petrocelli crouched beside a knocked-out M4A3 Sherman, its hull blackened from fire, its crew long since evacuated or worse. The air smelled of diesel fuel and scorched metal. Around him, 3 other men from the 3rd Army's Maintenance Battalion worked with cutting torches, the blue-white flame throwing dancing shadows across the snow. They were stealing. Not supplies. Not rations. They were cutting away the front glacis plate of this dead Sherman, all 51 millimeters of it, angled at 56 degrees, and they would weld it directly onto the front of another tank. A tank that was still fighting. This wasn't in any manual. This wasn't authorized by ordnance. But it worked. And in the arithmetic of survival that dominated the winter of 1944 and 45, that was the only equation that mattered. The question, at the heart of this story, is not whether American ingenuity could solve problems. History had already answered that. With landing craft, atomic bombs, and assembly lines that buried the Axis in materiel. The question is darker, more troubling. Why did American tank crews have to solve this problem themselves? Why were men with cutting torches and welding rods doing what factories and engineers should have done 2 years earlier? If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This is not a story about a single miraculous innovation. This is the story of a systemic failure, of institutional blindness, and of the grim pragmatism that emerges when men realize that doctrine and reality have diverged so completely that survival requires disobedience. To understand why Petrocelli and thousands of men like him were field-modifying their Shermans in the winter of 1945, we must first understand what the Sherman was supposed to be and what the men who built American armor doctrine believed about modern war. The M4 Sherman medium tank entered production in February 1942. Its design reflected a coherent philosophy, one that made sense in the context of 1941, when the specifications were finalized. The United States Army Ordnance Department designed the Sherman to be mechanically reliable, easily mass-produced, simple to maintain, and capable of performing multiple roles on the battlefield. It would carry a 75mm gun, suitable for engaging enemy armor, fortifications, and infantry. It would be fast enough to exploit breakthroughs. It would be simple enough that American industry could build it by the tens of thousands. And they did. Between 1942 and 1945, American factories produced over 49,000 Shermans in various configurations. The tank was designed around the 10 Continental R 975 radial engine, though variants would use everything from twin General Motors diesel engines to Ford's purpose-built GAA V8. The transmission was reliable. The suspension, based on a vertical volute spring system, was durable. The tank could be repaired in the field with standard tools. These were not small achievements. The Sherman's armor protection reflected a specific set of assumptions about how tank warfare would unfold. The hull front, the glacis plate, was 51 millimeters thick, sloped at 56 degrees from vertical. This slope increased the effective thickness to approximately 91 millimeters against projectiles striking at perpendicular angles. The turret front was 76 millimeters thick, angled at 30 degrees, with an additional 51 millimeter gun shield. The sides were 38 millimeters. The rear was 38 millimeters. The top was 19 to 25 millimeters, enough to resist artillery fragments but not direct hits. These numbers were not arbitrary. They were calculated to defeat the primary threats American planners expected the Sherman to face. The German Panzer III, with its 50 millimeter gun, the Panzer IV, with its short-barreled 75 millimeter gun, and various anti-tank guns of similar caliber. Against these weapons, at typical combat ranges of 500 to 1,000 yards, the Sherman's frontal armor was adequate, not impervious, adequate. American tank doctrine in 1942 reflected the lessons, or what were believed to be lessons, of the North African campaign and the broader principles of mobile warfare. Tanks were not primarily designed to fight other tanks. That was the job of tank destroyers. fast, lightly armored vehicles with powerful guns, designed to ambush enemy armor. Tanks were meant to exploit breakthroughs, support infantry, destroy fortifications, and maintain momentum. If they encountered enemy armor, they would fix it in place, and call for tank destroyers or artillery. This doctrine was not stupid. It was based on reasonable assumptions about the nature of industrial warfare and the proper division of labor in a combined arms battle. The problem was that the German army had not read the American doctrine manual, and by the summer of 1944, when American armored divisions finally encountered the Wehrmacht in large-scale combat in Western Europe, the assumptions underlying that doctrine had become catastrophically obsolete. The Germans had introduced the Panzer V Panther in the summer of 1943, following their devastating losses at Kursk. The Panther mounted a 75mm KWK 42 litres, 70 gun, a high-velocity weapon capable of penetrating 140mm of armor at 1,000 meters. Its frontal armor was 80 to 100mm thick, sloped at 55 degrees, giving an effective thickness of over 140mm. A. Sherman's 75mm gun, firing M61 armor-piercing capped ballistic cap ammunition, could penetrate 94mm of armor at 500 yards and 83mm at 1,000 yards. Against a Panther's frontal armor, the Sherman's main gun was nearly useless except at point-blank range, and even then, only against specific weak points, like the gun mantlet. The Panther could kill a Sherman from 2,000 meters. The Sherman could barely scratch a Panther from 500 meters. The Tiger I, which had been in service since late 1942 but was deployed in greater numbers by 1944, was even more formidable. Its 88mm KWK 36 litres, 56 gun, could penetrate the Sherman's frontal armor from well over 2,000 meters. Its frontal armor, 100mm thick, was effectively immune to the Sherman's 75mm gun at any range. These were not rare, exotic vehicles. By June 1944, the Wehrmacht had deployed hundreds of Panthers and Tigers on the Western Front. They formed the core of SS Panzer divisions and were attached to Wehrmacht Panzer divisions in increasing numbers throughout the autumn and winter. American tankers discovered this reality in Normandy. The terrain of Normandy, the Bocage country, was a nightmare ground for armor. Centuries of agricultural development had divided the landscape into small fields, surrounded by thick hedgerows, dense tangles of earth, roots, and vegetation, sometimes 6 feet high and equally deep. Roads were sunken lanes, narrow and easily blocked. Visibility was measured in yards, not miles. It was perfect defensive terrain. German doctrine, flexible and adaptive even in retreat, exploited this ruthlessly. Panzer units would position a single tank or anti-tank gun to cover a likely avenue of approach, let American armor advance into visual range, and open fire. The first shot usually killed the lead Sherman. The terrain made flanking maneuvers difficult and time-consuming. American units would call for artillery or air support, but in the close terrain, these were often ineffective or risked hitting friendly forces. The after-action reports from Normandy are grim reading. The 2nd Armoured Division reported that in engagements with German armour, Sherman crews felt outgunned and underprotected. The 3rd Armoured Division noted similar concerns. By late July 1944, 1st Army had begun receiving reports of declining morale among tank crews. Some men were requesting transfers to infantry units, reasoning that a foxhole offered better protection than a Sherman. This was unprecedented. Armour had always been considered an elite branch, offering better food, more mobility, and relative protection compared to infantry. The fact that men were volunteering to leave their tanks spoke to a profound crisis of confidence. The Army's initial response was to suggest tactical solutions. Tank-infantry cooperation was emphasized. Units were instructed to use terrain more effectively, to advance more cautiously, to employ reconnaissance more thoroughly. These were reasonable suggestions, and they helped at the margins. But they did not address the central problem. American tanks were being consistently defeated by German armor in direct engagements. Some solutions were already in the pipeline. The M4A3E2 assault tank, later nicknamed the Jumbo, entered production in May 1944. It featured substantially increased armour, 102 mm on the hull front, 152 mm on the turret front. It could withstand frontal hits from the 88 mm gun. But only 254 Jumbos were built, and they were distributed sparingly across armoured divisions. Most Sherman crews never saw one. The 76 mm gun, mounted in a new turret, offered improved anti-armour capability. The M1 76 mm gun could penetrate 109 mm of armour at 1,000 yards, using M62 APCBC ammunition. This was a significant improvement, but it still couldn't reliably penetrate a Panther's glacis plate. And the 76 mm Shermans only began reaching frontline units in significant numbers in August and September 1944, months into the campaign. For most crews, through most of 1944, the solution to the armour problem would have to come from elsewhere, or from themselves. The practice of adding improvised armour to tanks was as old as armoured warfare itself. In World War I, crews had hung spare track links, sandbags, and scavenged metal on their vehicles. The impulse was understandable: more mass between you and the incoming shell. But the effectiveness of such measures was questionable. In Normandy, tank crews began loading sandbags onto their Shermans. The practice spread rapidly. Some units developed elaborate systems: wooden frameworks welded to the hull to hold sandbags in place, 2 to 4 bags deep on the glacis plate, 2 deep on the sides. Some tanks carried up to 170 sandbags. The psychological benefit was real. Crews felt better with anything between them and German guns, but the actual protective value was minimal. The U.S. 7th Army conducted tests in August 1944. They fired captured German weapons at sandbagged mock-ups. The results were discouraging. Sandbags did almost nothing to stop armour-piercing rounds. The projectiles simply punched through. In some cases, the added mass actually made penetration easier by preventing the shell from ricocheting. A round that might have glanced off the sloped glacis plate would instead strike a sandbag, be slowed slightly, rotate downward, and hit the armour plate at a more perpendicular angle, exactly the angle that maximised penetration. General George S. Patton, commanding 3rd Army, reviewed the test results and issued an order banning sandbags on tanks in his command. The order was resented by many crews, who felt safer with the bags, regardless of what the tests showed. But Patton was insistent. The bags added weight, reduced mobility, increased fuel consumption, and provided no real protection. They were, in his assessment, a dangerous illusion. The same tests found that concrete, another popular improvised armour material, was equally ineffective. Some units had poured 3 to 4 inches of concrete onto their glacis plates. The concrete cracked under the stress of combat movement and offered negligible resistance to armour-piercing rounds. But one improvised modification did work. In September and October 1944, as the 3rd Army pushed through Lorraine toward the German border, maintenance units began experimenting with a different approach. Instead of adding soft materials like sandbags or concrete, they would add real armour plate salvaged from destroyed tanks. The logic was simple. By late 1944, there were plenty of knocked-out Shermans. Some had been hit in the engine compartment and gutted by fire, but their hull armour was intact. Some had been hit in the sides or rear. Some had struck mines that destroyed the suspension, but left the upper hull largely undamaged. These hulls represented a resource: factory-quality armour plate, already shaped and heat-treated, just waiting to be reused. The process was labour-intensive. A maintenance crew would locate a destroyed Sherman with salvageable armour. Using cutting torches, they would remove the front glacis plate, the large, angled section that formed the upper hull front. This plate, on later model Shermans, was a single piece of 51 mm rolled homogeneous armour, angled at either 56 or 47 degrees depending on the hull type. It weighed hundreds of pounds. The salvaged plate would be transported to a maintenance area, cleaned and inspected for cracks, or heat damage. If it passed inspection, welders would then attach it to the front of an operational Sherman. The attachment method varied. Some crews welded the plate directly onto the existing glacis, creating a double-thickness frontal armor. Others welded spacer blocks first, creating a small air gap between the original armor and the added plate. The air gap, it was theorized, might help dissipate the force of impact or cause projectiles to tumble. The modification increased the effective frontal protection to roughly 100 to 110 millimeters of armor, depending on the exact configuration and how the angles stacked. This was still not enough to stop a Panther's gun at all ranges, but it significantly improved the protection against the long-barreled 75mm guns on late-model Panzer IVs, and it offered at least a chance of deflecting or breaking up projectiles from more powerful weapons at longer ranges. The modification was not officially sanctioned by ordnance. There was no technical manual describing the procedure. There was no official supply chain for salvaged armor plates. This was field expedience, pure and simple. But it worked. Third Army units, operating under Patton's pragmatic leadership, embraced the modification enthusiastically. Maintenance battalions set up assembly lines of sorts, processing multiple tanks per day. By late November 1944, a substantial percentage of Third Army's M4A3S and even some M4A1S had been up-armored with salvaged plates. The modification had drawbacks. It added roughly 1 to 1.5 tons to the tank's weight, concentrated on the front. This increased ground pressure slightly and reduced maximum speed by perhaps 2 to 3 miles per hour. It increased fuel consumption. The additional weight put more stress on the transmission and final drives, potentially reducing mechanical reliability. The added frontal weight also altered the tank's balance, which could affect handling on slopes or rough terrain. But tankers accepted these trade-offs without hesitation. Speed and fuel economy meant nothing if you were dead. A slightly overtaxed transmission was preferable to a penetrated hull. The modification's effectiveness was documented in after-action reports from late 1944 and early 1945. Units reported instances where up-armored Shermans had taken frontal hits that would have penetrated a standard tank but were instead defeated or partially defeated by the double-layer armor. The projectile would penetrate the outer plate, lose velocity and structural integrity, and fail to penetrate the inner plate, or would penetrate both, but with reduced post-penetration effects, giving the crew time to bail out. These were not miraculous saves. The modification did not transform the Sherman into a tiger, but it tilted the odds slightly, and in combat, slight improvements in survival probability compound over time. A crew that survives one engagement fights in the next one, accumulating experience, becoming more effective. A tank that remains operational contributes to the unit's combat power. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The salvaged armor modification raises an uncomfortable question. Why hadn't ordnance done this from the factory? The answer is complex, involving bureaucracy, logistics, doctrine, and the inherent conservatism of military institutions. Increasing armor thickness was not a new idea. Ordnance had been receiving requests for heavier armor since late 1943, when reports from the Mediterranean theater first highlighted the Sherman's vulnerability to newer German weapons. The problem was that simply adding armor to the existing design had cascading effects throughout the vehicle. Part 2. Adding 50mm of armor to the front of a tank sounds simple. In practice, it meant redesigning the suspension to handle the additional weight. It meant upgrading the transmission to handle the increased load. It meant modifying the engine cooling system because the added weight would generate more heat. It meant recalculating ground pressure and potentially widening the tracks. Each of these changes required engineering time, testing, retooling of production lines, and coordination across multiple manufacturers. The United States had 11 different companies building Sherman variants during the war. Chrysler, Ford, Fisher, Tank Arsenal, Pacific Car and Foundry, Pressed Steel Car Company, Lima Locomotive Works, American Locomotive Company, Baldwin Locomotive Works, Federal Machine and Welder, Pullman Standard, and Montreal Locomotive Works in Canada. Each factory had its own tooling, its own supply chains, its own variants. Implementing a major design change across all these facilities would take months, and there was the fundamental question: was it worth it? By mid-1944, the United States had already built over 30,000 Shermans. The factories were producing them at a rate of over 1,000 per month. The supply chain, spare parts, ammunition, training programs, maintenance manuals was built around the existing design. Changing the design meant orphaning thousands of existing tanks, creating a logistics nightmare where different units would require different parts, different ammunition loads, and different maintenance procedures. From a systemic perspective, Ordnance's caution made sense. The Sherman, for all its vulnerabilities, was winning. The Allied advance through France had been rapid. German forces were in retreat. The strategic situation suggested that the war might be over by Christmas 1944. Why disrupt production for a threat that might be obsolete in months? This was the calculus of distant planners, working from casualty statistics and operational maps. It was not the calculus of men inside tanks. The Battle of the Bulge shattered any remaining illusions about the war being nearly over. On December 16, 1944, German forces launched Operation Wacht am Rhein Watch on the Rhine, a massive counter-offensive through the Ardennes forest. The attack involved 3 German armies, over 200,000 men, nearly 1,000 tanks and assault guns, and 2,000 artillery pieces. The Germans achieved complete tactical surprise. Allied forces in the Ardennes sector were thin, consisting largely of units recovering from earlier battles or newly arrived divisions still acclimatizing to combat. The offensive was spearheaded by SS Panzer divisions equipped with Panthers and Tigers. These formations smashed through American defensive positions, creating a bulge in the Allied lines, hence the battle's name. American units fought with desperate courage, but the material disparity was stark. Sherman-equipped tank battalions found themselves engaging Panthers and Tigers under conditions that maximized German advantages: surprise, momentum, and the close terrain of the Ardennes forests and villages. The 7th Armoured Division, fighting in and around Street Veith, lost dozens of Shermans in the first days of the battle. The 10th Armoured Division, defending Bastogne, reported similar losses. After-action reports describe Panthers firing at ranges of 800 to 1,000 meters, knocking out Shermans before American crews could effectively return fire. In village fighting, where ranges were shorter, American crews had better odds, but the Germans had learned to position their armor defensively, hull down behind rubble or at street corners, maximizing their guns' advantages while minimizing their exposure. The casualty rates among American tank crews during the Bulge were the highest of the European campaign. Some companies lost 50% or more of their tanks in the Pacis first week. Crew casualties killed, wounded, or severe burns were proportionally even higher, as penetrating hits often caused catastrophic fires when the ammunition storage was breached. The Battle of the Bulge did not change American tank doctrine overnight, but it did change the institutional attitude toward field modifications. As Third Army units counterattacked north toward Bastogne in late December, Patton's staff explicitly encouraged the salvaged armor modification. Maintenance battalions were given priority access to destroyed tanks. Welding teams worked around the clock. The modification, which had been tolerated in autumn, became actively promoted in winter. Other armies and army groups took note. By January 1945, 1st Army and 9th Army units were also implementing salvaged armour modifications, though less systematically than 3rd Army. British units attached to American armies began modifying some of their Sherman Fireflies Shermans regunned with, the British 17-pounder using similar techniques. The modification became part of the informal knowledge base that combat units develop, passed along through maintenance officers, shared at repair depots, discussed in the careful language of men who know they are technically violating regulations, but also know that survival trumps paperwork. There were other modifications as well, beyond armour. Some were official, like the Cullen hedgerow cutter, a device invented by Sergeant Curtis G. Cullen of the 2nd Armoured Division, consisting of scrap metal welded to the front of the tank to cut through hedgerows. Over 500 Cullen devices were manufactured in the field in June 1944, and the modification was officially endorsed by the First Army. It was a rare example of field innovation being rapidly adopted by institutional authority. Other modifications remained informal. Crews welded spare track links to vulnerable spots on the hull and turret. While tests showed this was less effective than proper armor plate, it provided some psychological comfort and might deflect small arms fire or shrapnel. Crews modified their machine gun mounts for better anti-aircraft coverage. They added storage racks for additional ammunition, food, and personal gear. They camouflaged their tanks with whatever was available: mud, foliage, whitewash in winter. These modifications transformed the Sherman from a factory product into something more personal, more adapted to the specific conditions of combat. A late-war Sherman in a veteran unit was often barely recognizable compared to the clean, standardized vehicle that had rolled off the production line. It was covered in tools, spare parts, improvised armor, camouflage, unit markings, and personal touches, names painted on the barrel, kill rings, good luck charms welded to the turret. This process of adaptation was not unique to the Sherman. German tank crews did the same thing with their Panthers and Tigers, adding Zimmerit anti-magnetic paste, spare track links, camouflage, and improvised field repairs. Soviet crews modified their T-34 seconds extensively. The British modified their Cromwells and Churchills. What was perhaps unique about the American experience was the scale, the sheer number of tanks involved, and the industrial capacity to support field modifications with cutting torches, welding equipment, and salvaged materials. By February 1945, as Allied forces crossed the Ruhr River and advanced toward the Rhine, the Sherman's vulnerability to German armor was becoming less relevant for a different reason. There were fewer German tanks left. The Battle of the Bulge had cost the Wehrmacht dearly. The offensive consumed Germany's last significant strategic reserves of armor, fuel, and trained crews. The Luftwaffe, which had provided limited air cover for the offensive, suffered crippling losses. In January and February, as German forces retreated back to the Rhine, they abandoned hundreds of tanks and assault guns due to fuel shortages or mechanical breakdowns. Allied air superiority, which had been temporarily challenged during the Bulge's opening days due to bad weather, reasserted itself completely. Jabos Allied fighter bombers hunted German armor relentlessly. Panthers and Tigers, for all their formidable armor and firepower, were as vulnerable to air attack as any other vehicle. Rockets, bombs, and even heavy machine gun fire could disable tanks by destroying tracks, engine compartments, or optical equipment. By March 1945, when Allied forces crossed the Rhine and began the final drive into Germany, German armoured resistance had collapsed. Sherman crews were more likely to encounter Panzerfausts, handheld anti-tank weapons used by German infantry, than actual tanks. The salvaged armour modifications, ironically, became less necessary, just as they became most common. The war in Europe ended on May 8, 1945. In the final accounting, the United States had built 49,234 Shermans. Approximately 8,000 were total losses in the European theatre, destroyed beyond recovery. Thousands more were damaged and repaired, some multiple times. American tank crew casualties in Europe totaled approximately 3,000 killed and over 10,000 wounded. These numbers, while significant, were far lower than infantry casualties, and the Sherman's mechanical reliability meant that strategic mobility was maintained throughout the campaign. The Sherman had won, in the sense that the armies equipped with it had won. But the victory came at a cost that extended beyond the casualty lists. The debate over the Sherman's adequacy began even before the war ended, and has continued, in various forms, for 8 decades. Critics argue that the Army should have fielded the M26 Pershing heavy tank earlier, or adopted the 76mm gun sooner, or increased armor protection years before it happened. Defenders argue that the Sherman was fit for purpose, that its mechanical reliability and ease of production outweighed its combat limitations, that American combined arms doctrine meant tanks didn't need to win duels with Panthers because artillery and air power would handle German armor. Both arguments contain truth. Both miss something essential. The salvaged armor modification is important not because it was a silver bullet, it wasn't, but because it reveals the gap between institutional planning and tactical reality. The men cutting plates from dead Shermans and welding them onto live ones were solving a problem that, from Ordnance's perspective, didn't need solving. The production numbers were good. The strategic advance was proceeding. Casualties were within acceptable parameters. The system was working. But systems are built on aggregates. They see numbers, not faces. A 5% attrition rate on paper is, for the men inside, those 5% of tanks, a 100% casualty rate. The crews who modified their tanks were not rejecting American doctrine or technology. They were refining it, adapting it, making it work under conditions the planners hadn't fully anticipated. They were demonstrating a principle that military institutions always struggle with. The people closest to the problem often see solutions that distant authority misses. This tension between institutional inertia and tactical innovation is not unique to World War II or to armored warfare. It appears in every military conflict, in every complex organization. The question is whether the institution can recognize and incorporate field innovations quickly enough to matter. In the case of the Sherman, the answer was mixed. Some innovations, like the Culin hedgerow cutter, were rapidly adopted. Others, like the salvaged armor modification, remained semi-official, tolerated but never standardized. Still others, like the Cruise, preference for the 76mm gun, took months of lobbying and after-action reports before policy changed. What remained consistent was the ingenuity of the crews themselves. Given cutting torches, welding rods, and salvaged materials, they built what they needed. Given impossible odds, they found ways to survive. Given tanks that institutional authority declared adequate, they made them better. Staff Sergeant Michael Petrocelli, the maintenance NCO we met at the beginning of this story, survived the war. His unit, part of 3rd Army's 10th Armoured Division, crossed the Rhine at Oppenheim in March 1945 and drove deep into Bavaria. The Shermans, he had up-armoured 17 in total between January and March, all survived to the surrender, though several had been damaged and repaired multiple times. 3 of his modified tanks were hit by German anti-tank weapons during the fighting around Nuremberg. In each case, the double-layer frontal armour worked as intended. The outer plate was penetrated, the inner plate held, and the crew survived to fight another day. After the war, Petrocelli was interviewed as part of the Army's Operational History Project. When asked about the field modifications, he was characteristically direct. "We did what we had to do. If Ordnance had given us better tanks, we wouldn't have needed to cut up the old ones. But they didn't, so we did." That simple statement captures something essential about the American experience in World War II. The United States won not just through industrial capacity or technological sophistication, but through the practical problem-solving ability of millions of individuals who refused to accept that the way things were done was the only way they could be done. The Sherman tank, in its standard factory configuration, was a competent but flawed vehicle. The Sherman tank, as modified, adapted, and personalized by the men who fought in it, became something more, a testament to human ingenuity under pressure, to the willingness to take risks when regulations offered no safety, to the recognition that survival sometimes requires breaking the rules. The salvaged armor modification was not a miracle. It did not transform the Sherman into a tiger, but it saved lives not through any single dramatic moment, but through the accumulated small advantages of slightly better protection, slightly better odds, slightly more time to react or escape. In the brutal mathematics of armoured combat, these small advantages compound. And in the end, that was enough. The crews who welded those plates onto their tanks understood something that planners often forget. Perfect is the enemy of good enough, but good enough is the enemy of death. They needed tanks that gave them a fighting chance. They built those tanks themselves, one welding bead at a time, from the wreckage of machines that had failed to protect their previous crews. It was pragmatic. It was unauthorized. It was necessary. And it worked. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.